The study of curved spherical forms through the perspective of cylindrical geometry allows for a comprehensive understanding of how three-dimensional space is occupied and measured. This approach reimagines the surface and interior of a sphere by looking at it as a series of expanding circular layers. The core problem and surface measurement. The primary challenge addressed in the sources is the parameterization of a half-sphere to determine its total surface area. Instead of using traditional angles from the center, this method uses coordinates that describe a point's distance from the central axis and its rotation around that axis. By calculating how these coordinates change as they move along the curved surface, we can define a metric that accounts for the shape's curvature. This metric allows us to find the size of a tiny patch of area anywhere on the dome. When these patches are summed up across the entire surface, the result is exactly half of the area of a complete sphere. The geometry of stretching. A key conceptual takeaway is the relationship between different ways of measuring a sphere. The cylindrical approach essentially treats the process as stretching a flat, circular disk from a horizontal base until it perfectly covers the dome. Because the sphere becomes increasingly steep as it approaches its equator, a correction factor is used to ensure the measurements remain accurate even as the surface becomes nearly vertical. This method ensures that the final geometric results are identical to those found using standard spherical measurements. Measuring internal space. The same logic is used to calculate the volume, or the internal space, of the hemisphere. This involves measuring the space between a flat base and the curved ceiling of the sphere. The calculation starts at the very center and moves outward, accumulating space in a way that highlights the cubic nature of volume. The final result confirms that a hemisphere contains exactly half the volume of a full sphere. Variation. The spherical cap. The sources also explore the spherical cap, which is a portion of a sphere cut off by a flat plane. The primary difference in this example is the boundary of the measurement. Rather than expanding to the sphere's full width, the calculation stops at the specific radius where the slicing plane meets the sphere's curve. The formulas for the area and volume of this cap are specifically determined by the total size of the sphere and the height at which the cut was made. Visualizing the construction. To make these abstract calculations easier to understand, the sources describe digital animations that build these shapes piece by piece. These demonstrations show the volume accumulating as a radial boundary sweeps outward. In these visualizations, three distinct elements are shown coming together. A curved top surface that defines the sphere's outer shell. A flat base representing the slicing plane. A growing vertical wall that acts as the current limit of the calculation. By watching these elements interact in real time, one can see how the total space is filled, transforming complex mathematical integration into a clear, visual construction of a geometric object.